Hi, ladies and gentlemen. We're going to be talking about oxidation reduction reactions today. We also like to call these redox reactions sometimes. And these are basically going to be involved with the transfer of electrons from one element to another element, one atom to another element. We're going to transfer electrons. So let's take a look at a sample problem first, and we're going to talk about two different ways that we can approach the same thing. So we have a sample here. We have solid calcium, and it's going to react with 2 molar hydrochloric acid solution. And so let's write a complete complete equation for this first. Solid calcium plus HCl. And what's going to happen here is this type of reaction we call an oxidation reduction reaction, but we also call it a single replacement reaction. Essentially, the metal is going to replace the metal. So calcium is going to go with chlorine. Calcium forms a 2+ charge, chlorine a 1-. So we have calcium chloride. It's going to be an aqueous solution because it's got a chloride in it. Chlorides are soluble except when they're with silver, mercury, and lead. So we're gonna ionize that guy in a little while. Now the hydrogen gets knocked off by itself, and whenever hydrogen is knocked off by itself, and it is not an ion, we write it as diatomic, and we call it hydrogen gas. And in this case, this reaction, hydrogen gas, is produced, and it typically is produced in a single replacement reaction if it's one of the products by itself. Now what we're going to do is go through and ionize everybody. We're going to take calcium, it's a solid. We leave it as a solid, no ions or anything like that on it. Hydrogen ion plus the chloride ion, we ionize both of these guys because this is a strong acid. Calcium chloride, we said before, we are going to ionize this. And then the hydrogen gas is a hydrogen gas, so we do not ionize that. And so we can now go through and we can eliminate our spectator ions, which in this case are going to be our chloride. And so we have calcium plus hydrogen yields calcium ion plus hydrogen gas. So let me rewrite that. So it just is a little bit cleaner, and we can work with it a little bit easier. We're going to balance this guy here, and so we have 2 hydrogens there. So now we're all nice and balanced. And what we're going to do is there's a couple ways to address what's happening here. And we're trying to figure out where the electrons are coming and going to and from and things like that. So what we're going to do is we're going to write what are called half reactions first. And this is one of the ways to determine where the electrons are being lost and gained. There's another way, which we'll talk about in a few minutes here, so for half reactions. So what I'm going to do for a half reaction is I'm just going to take my calcium first. And so I have calcium solid, which is a neutral compound, or neutral atom. It's got equal number of protons and electrons, and I know it does because it does not have a charge. And then over here I have a calcium 2+, and the reason why it becomes a 2+ is it has lost 2 of its electrons. And I know it's lost 2 because it's got a 2+ charge here. Okay? Now, what we say is we go from a neutral calcium to losing 2 electrons. So this is going to be what we call loss. Loss of electrons, and the definition is when you lose electrons, we're going to call you oxidation. That is the definition of oxidation, is the loss of electrons. And so we use this in this little LEO, we call it LEO, loss of electrons, oxidation, LEO. Okay, and we'll talk about that in a second. Let's go. You might be thinking to yourself, where are these electrons going? Well, somebody's got to gain them. And so over on the other side of our other half reaction, we're going to take a look at our hydrogen from our original reaction up here. And so let's take our 2 hydrogens, which are positively charged, and then we're going to put an arrow, and then we have H2 gas over here. And so what happens is right here, we're going to gain 2 electrons, and once we have 2 more electrons, that becomes neutral, and then we have our hydrogen. So we're going to say gain of electrons is reduction. And so GER is our little mnemonic. So these 2 mnemonics of which I'm talking about here is LEO, loss of electrons, oxidation, says GER. And you can imagine if you have a lion, his name's Leo, and he's going to say GER. Leo says GR, and so that is our little mnemonic that we're going to use to remember loss of electron is oxidation, gain of electron is reduction. And I didn't make that up. Everybody knows loss of Leo says GR. What we just talked about is using our half reactions to determine who is being oxidized and who's being reduced, oxidation and reduction. There's another way to take care of that, and we're going to call this oxidation numbers. And oxidation numbers are used to keep track of electrons. And there's about 6 different rules, and then I'm going to show you some practice problems on oxidation numbers, and then we'll show you how this applies to keeping track of electrons, whether they're being lost in oxidation or gained in reduction. So let's talk the rules first. And these rules are kind of arbitrary. They're just rules that only apply for oxidation numbers, although you see there's going to be a little overlap in some other things. Now, the first thing is we're going to talk about an atom in its elemental form has an oxidation number of 0. What we mean by elemental form is how an atom would exist in nature, and here's a couple examples. Let's say hydrogen gas, which is what would how hydrogen exists in nature. We would say that each hydrogen has an oxidation number equal to 0. P4, which is phosphorus, again, each phosphorus would have an oxidation number equal to 0 because that's its elemental form. Okay, and there's going to be more rules, so we'll come across some of those. That's the first one. Second one. For our monoatomic ion that we have, any monatomic ion is going to have a charge. And so usually, the charge is going to equal the oxidation number of that ion. So, for example, let's say we have potassium, and potassium forms a 1+, we would say that potassium has an oxidation number of a +1. And you might remember way back in regular chemistry when we started talking about charges on ions, we said we always write them with the number first and then the charge. Well, this is the reason why. Because this means charge, where this means oxidation number is 2 different things. Sulfide would obviously have a -2 charge. Okay? Oxygen is usually a -2 because oxygen or oxide, when it forms an ion, is 2-. There's an exception to this rule, except if you have peroxide, and peroxide is O2 2-, and so each oxygen has a -1 charge to give an overall charge of a -2 on this guy. Hydrogen itself is the next rule. Hydrogen is usually a +1. If you remember, hydrogen mostly forms a 1+. Hydrogen also has the ability to bond to other metals. And in this case, we call it a hydride. In this case, it's a -1. But that's a pretty rare scenario. Usually we say hydrogen is a +1. Halogens are usually -1, those 7As. And probably the most important rule of them all we add up all of our oxidation numbers, and there's 0 in a neutral compound. And they're equal to the charge in an ion. And this will make sense here in a couple of minutes when we take a look at some charged ions. So let's talk about